Any questions from the last class? From the previous classes? So there were two major rotation schemes we discussed. The direction cosine matrix and the Euler angle and Euler axis. So if I remember, we had come to this location where we had to prove certain properties of the rotation matrix. Do you remember if we stopped here or before this? I think we discussed these exercises, right?
Yes, sir.
Okay. So direction cosine matrices, why is the name called so?
Because the matrix contains the direction cosines.
Very good. And then the matrix is used for what? Transforming
Coordinate systems. Very good.
from one coordinate system to another coordinate system. The matrix which transforms one coordinate system to another coordinate system contains the direction cosines of the vectors under consideration. That is one. Then in the case of Euler angle and Euler axis, what was important? Is the sequence important?
Yes, sir.
Very good. So if you do not follow the sequence, even though you follow the corresponding angles for the axis, you may end up with the wrong or different orientation. So sequence is very important. And another way to look at the importance of sequence is the composition of rotations. If you are doing multiple rotations, the overall rotations is expressed as a composition of the individual rotations. So individual rotations are represented by matrices. So composite of rotations will be multiplication of these matrices. Matrix multiplication is non-commutative. So we see the non-commutative effect. Once you change the sequence, the multiplication sequence has to change. There, since the matrix multiplication is not commutative, you can expect the rotation sequence also to be non-commutative. That means it is important to follow the sequence. If the sequence is changed, then you can expect the orientation also to change. So today we will discuss some properties for the rotation matrices. We have already discussed that it is an orthogonal matrix and we have indicated that it has determinant 1, but we have to now formally prove that these results are true. So one of the abstract way to express a rotation matrix is that the length of the rotation vector does not change. This is one of the important property in a rotation operation. Not only that, the scalar product of two vectors before rotation and after rotation remains same. That is, scalar product is invariant under rotation operation. So using these two properties, one can state that this is a rotation operation. That's what we are going to do now. So let us see what properties can be derived from these two statements. These are the hypotheses. From these hypotheses, we will come out with the proofs. So first what we will do, even though we have already shown it is orthogonal, we will once again show that these two properties can give the orthogonal property back. Yes? Yeah.
So the scalar product here means dot product, right?
Yeah, dot product, both are same. Scalar product. In Euclidean geometry, it is called scalar.
So then,
There is a cross product also, that is why you call it as a scalar product.
okay, sir. It is in cross product then, not a dot product.
Yeah, this is dot product and scalar product are same.
Okay, sir. So then, if we have like if we do dot product of two vectors with different angles between them, they will be different, right? You have written the statement that scalar product of two vectors is invariant under rotation. So
two vectors means if when you say take scalar product, you take before the rotation you take scalar product and after rotation you take scalar product.
Both the vectors are rotating or only one vector?
Both will be rotated.
Okay, sir. Okay, fine.
Yeah, because the coordinate system itself is rotating, the scalar product you don't expect to change. Another way to look at it is we have already looked at that rotation of a vector and rotation of a frame. So rotation of a vector is equivalent to rotation of a frame in opposite direction. So by rotating the frame, you don't expect the dot product to change. So this dot product is an absolute quantity in the sense dot product between two vectors will remain same irrespective of what coordinate system you are going to use.
Yes, sir.
So that is another way to think of this. Okay, so here we are using this notion that you are going to rotate both the vectors and then see what is the dot product. And then before that, what was the dot product? These two quantities are same under this rotation operation. So suppose A is the rotation matrix and let V1 and V2 be the vectors. The second statement says that after rotation, the vectors are AV1 and AV2. The dot product after rotation is AV1 whole transpose AV2. And this should be equal to before rotation, which is V1 transpose V2. So once you equate this, you simplify, apply your linear algebra rules by using the associative property of the matrix, and then the transpose is expanded. All those things, once you do, you collect the terms on the left-hand side, and you also take out V1 and V2 common on the left and the right separately. Since V1 and V2 are any arbitrary vector, this expression is true for any vectors V1 and V2 in the R3 or the third three-dimensional space. Therefore, the central matrix has to be 0. So this means that A transpose A is identity. So even the statement, the scalar products are invariant, shows that the matrix should be orthogonal to each other. Okay, anyway, this we have already shown. Just for academic sake, we are doing it again to see how we can arrive at certain properties in so many different ways. But more than that, let us look at this, why it should have determinant equals to +1. So this we should carefully see. Because one of the examples for orthogonal matrix, let me share the screen with you. Just a moment. Today's date is 6th. So if you look at the 2 cross 2 matrix, 1, 0, 0, -1, is this matrix orthogonal? How will you check? What is A transpose A? Can one of you tell?
1, 0, 0, -1 and 2.
Yeah, 0 -1 multiplied by, if you multiply it, what will you get?
Then
No, the same, no? Yeah, +1 -1, sorry. Transpose, if you have a diagonal matrix, if you transpose, it won't change. You will get this the same. So A is orthogonal matrix. Do you accept? But A is not rotation matrix. You can go back and check, verify this. This is actually a reflection matrix. Okay, you can imagine in a third dimensional system, you can take in 3D, you can take A equals to 1, 0, 0, 0, 1, 0, 0, 0, -1. So this will reflect a vector about the plane xy, xy plane, reflection about. So this is also not rotation matrix. Can go back and verify. So therefore, it is important to see that why this rotation matrix should have this determinant equals to 1. So for that, we consider these two properties. Let this, not let, that is actually turns out to be true that determinant of A is equals to determinant of A transpose. So instead of expanding by row, if you expand by column on the transpose matrix, you get the same result. It doesn't matter, of course, you can expand by any rows or any columns. And then you have this product rule, determinant of AB equals to determinant of A into B. So let us look at this determinant of A square, since determinant of which can be expressed as determinant of A transpose into determinant of A. Why is this true? Because determinant of A square is determinant of A into determinant of A, but determinant of A is determinant of A transpose. Therefore, you can replace one of the determinant of A with determinant of A transpose. And now you take that A transpose inside again, you get determinant of A square is equal to determinant of A transpose A. But determinant of A transpose A, what is A transpose A? A transpose A is identity matrix because A is an rotation, orthogonal matrix, in fact. So therefore, determinant of A square is equal to 1, which means that it can be either +1 or -1. We have seen cases that whenever that reflection happens, it is -1. We have to make sure that for rotation, this -1 can never come out. So we will be proving it. So one of the intuitive way to understand is rotation preserves the handedness. So whichever handedness system you are in, that system's handedness is preserved when you rotate the vector. But however, when you saw that the determinant equals to -1 as certain examples, so if you go back to this expression and you have this matrix 1 0 0 0 1 0 and 0 0 -1, this actually will reflect the z-axis to -1 location. And if you look at that new coordinate system, you will notice that it is a left-handed system. That means when you take cross product of vector A and B, you won't get +1. You are using the minus direction of the z-axis. So that is a left-handed system. So whatever matrix we have shown here, this is a left-handed coordinate system. So this is one way to look, but we will prove it much more formally now using the continuity of the rotation operation. Okay, so let us prove that it is equals to determinant equals to +1. So consider a rotation matrix A and let V be an unit vector in the axis of rotation. So how do you imagine axis of rotation? For that, you look at these matrices which are shown here. If you are rotating with respect to x-axis, then you have these things. So similarly, y-axis, z-axis, you have different matrices. So one can also imagine rotation with respect to an arbitrary axis of rotation. So one of your exercises, if you remember, was to derive the expression for the rotation operation when the axis of rotation was arbitrary. This was the one we had earlier indicated. So this matrix, what is shown on the right-hand side, is a rotation matrix with axis V and angle phi. That whatever phi is indicated here. So this is how you have to imagine. In general, any matrix you can imagine having an axis as well as angle of rotation. So let the angle of rotation be theta. So what is known is that the rotation matrix preserves the length of the vector. That means even after rotation, the length of the vector is same as the one which it was before rotation. And we have seen that the determinant of A is ±1. That is what we derived recently. We have to see how better we can do than this. So let us consider this case. Let us consider a series of matrix A, which is AT, where T is greater than or equal to 0 or less than or equal to theta. That means t is between 0 and theta. Let AT represent the rotation matrix about the same axis V, but now the angle is between 0 and theta. Any angle between 0 and theta. There are hundreds of matrices between them. So each matrix can be written like this, AT, where t is between 0 and theta. It is very clear that when you substitute t equals to 0, it represents rotation by 0 degrees, which is nothing but the identity matrix. So A0 is your identity matrix. And then when you substitute t equals to theta, it represents your original matrix A, which was given to you. So this is one important observation. Rotation operation is a continuous operation. That means every rotation can be, any rotation by an angle theta can be obtained by smoothly starting from 0 angle up to the given angle theta. This is an important observation. This is the basis on which we will be able to show that the determinant has certain fixed value. The rotation operation or the rotation, any given rotation can be obtained slowly, can be obtained by continuously rotating from 0 to the given angle. For instance, let us go back to the examples for x-axis, y-axis, and z-axis. Then the things will become relatively clear here. So if you look at this, it is very clear that if you have to rotate by angle psi, you can gently, smoothly come from the angle 0 to the angle psi. So every intermediate angle can be touched upon. Basically, the rotation operation is a smooth operation. You can smoothly transit from one angle to another angle, 0 angle to the given angle. So what does this mean? So if you consider each of the matrices in between when you are doing this rotation, 0 to the angle psi in this case, or in the case whatever we are discussing, it is angle 0 to t. So every matrix AT is now the continuous function. That means when psi is continuously changing from 0 to the given angle psi, the components of this matrix is changing continuously. That is what we mean. That is, when the psi changes continuously from 0 to the given angle, the components are continuously changing because cosine, sine, and other whichever the constant functions are continuous functions. Any questions here?
Sir.
If you change psi continuously, the components are changing continuously. That is a very simple statement we are making. Basic statement. So, but what about the determinant now? So determinant is nothing but a combination of multiplication and addition and subtraction of the components of the given matrix. So if the components are smoothly varying, the determinant also will vary smoothly. If the components are smoothly varying, the determinant of the matrix will vary smoothly. Now look at this state.
So won't the determinant always be 1 here?
Yeah. So if you look at this case, the determinant has to be either +1 or -1. It can have only two values. There is no continuity between the results. Either it is +1 or -1. So if the determinant is smoothly changing, what is the only possibility now? You have to see at least one of the determinants you have to compute. If one of the determinants you know to be either +1 or -1, then every other determinant of this AT should be same.
+1 then.
Yes. The reason is if the matrix
Identity.
at 0 degree, you have A0. The determinant of A0 is determinant of identity, which is +1. So it has to be +1 throughout, because determinant can take only two values, either +1 or -1. You have started with +1, and determinant is a continuous function of the matrix A, and then the matrix A is continuously changing. So therefore, the determinant has to be +1. So this is the important argument which is used to show that determinant of the rotation matrices are +1. Okay, so what we have, basic assumption we have made, if you know this one, that is every rotation can be obtained by smooth transition. This is our intuitive observation. From this, we can show that the determinant of a rotation matrix is +1. Any question here?
No, sir.
Okay. Let us now look at the other properties of this rotation matrix. What are the eigenvalues and eigenvectors of this matrix? Let us see if we can compute at least some of them. Eigenvalues are roots of the determinant A minus lambda I. This is the basic definition. There is one more important factor, that the matrix A minus lambda I loses rank at the eigenvalues of A. What does it mean? When you say roots of determinant of A minus I, if lambda is the root of A minus determinant of A minus lambda I, then at the eigenvalues, the determinant of the matrix is 0. If the determinant of the matrix is 0, what does it mean? Is it a full rank matrix or a reduced rank matrix? Determinant and rank, how are they
Reduced
related?
rank.
Is a reduced rank. So if you have a reduced rank matrix, then this system of equations has the AX equals to 0. If you have an expression AX equals to 0, I will simply write it. Just give me a moment. If you have this expression AX equals to 0, A is a square matrix. If determinant of A equals to 0, that is determinant of A is 0, what does it imply? What can you say about the solution of this expression?
X can be any value.
No.
Previous.
It cannot be any value.
X is 0, 0, 0.
You should say non-trivial solution exists. Exist for star. What does it mean? So let us look at this equation. If this is your A matrix, and what is the solution now for this system? Implies only one solution. Trivial solution. Only trivial solution. That means the only solution for this system of equation is 0. Now what we are saying is, we are giving an example. Suppose you have this situation. So what is the determinant of this matrix? If this is your A, not equal to 0. If this is your A, determinant of A is 0. So for this system, 0, 0, what is the solution? X1, X2 is 0 and any value A, where A belongs to R. So this implies there exists a non-zero solution or non-trivial. So whenever determinant of A is 0, non-zero solution exists or rank deficient. How do you spelling deficient? DEF5? I don't know. Just check it. So it is rank deficient. Rank deficient matrices, we are talking about the square system now, has non-zero or non-trivial solution. So if lambda is the eigenvalue, so and a minus lambda I, the determinant is 0, then a minus lambda I is rank deficient. So that means a minus lambda I multiplied by x equals to 0 as a non-trivial solution. That implies there exists x not equals to 0 such that a minus lambda I x equals to 0. This is your Rn, okay? So this implies Ax equals to lambda times x. That is how your eigenvector comes out. This x is called this non-trivial. There may be many, okay? I'm just writing this non-trivial solution is called eigenvector. So this is what we are discussing here. The eigenvalues are roots of the determinant of a minus lambda I. Once you say it is roots of determinant, that means the determinant is 0 at those locations. That means the matrix A minus lambda I loses rank at the eigenvalues of A. So these are called eigenvalues. So let us look at this expression now. We are going to see if we can construct at least one eigenvalue. So determinant of A and A transpose are same. That is equal to 1. So let us consider this determinant of A minus identity. So what happens? Determinant of A minus identity is equal to 1. You can simply multiply it with 1. That 1 means determinant of A transpose, which is also equal to determinant of A transpose multiplied by determinant of A minus identity. There is nothing wrong we have done because determinant of A transpose is always already 1 we have shown. So if you expand by using the product rule instead of expansion, now you are simplifying. You are taking this A transpose inside. Once you take it inside, you see determinant of A minus I is equal to determinant of I minus A transpose. So let us see how we can handle this I minus A transpose. I minus A transpose is nothing but minus of A transpose minus I and minus of A minus I whole transpose, because identity matrix is already symmetric. So therefore, determinant of A minus I is minus times determinant of A minus I whole transpose, which is equal to determinant of A minus I minus times determinant of A minus I. Minus will come out only for odd matrices. Okay, so let us observe this thing slightly more carefully. But determinant of A minus I whole transpose is nothing but determinant of A minus I itself, because transpose is not playing any role. So when will you get this condition that the number and its negative are same?
0.
Only when the number is 0. So that means determinant of A minus I is 0. So what does it indicate?
The lambda.
You look at this. What do you conclude when you say determinant of A minus I is 0, and then I have highlighted a line? So yes,
lambda multiplication of lambda equal to 1.
yes. So one of the eigenvalues of the rotation matrix is always 1. One of the eigenvalues of a rotation matrix is always 1. And this is only for odd systems, okay? This is true only for odd systems. Let us see why it cannot be true for even systems. Let us take an example. So consider A equals to minus 1, 0, 0, minus 1. Okay, so this is clearly equal to minus 1, 0, 0, 1. This is okay.
Yes, sir.
So now what is determinant of A?
One.
Determinant of -1, 0, 0, -1.
One.
This is determinant of -1, 0, 0, 1. So can you take this minus out here?
No, sir.
We cannot take. So that is what. Oh, sorry. This -1, this negative, we cannot take it out. For even ordered system, this is even. And if you consider the odd order, you let A equals, this is just an example, okay? So there it is a very generic case. -1, 0, 0, 0, -1, 0, 0, 0, -1. Here clearly determinant equals to -1. So in this particular case, I can take this as determinant of minus times determinant of 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is allowed for odd order. So that is what we have used here. So this property holds good for odd order system. And then you have this rotation operation defined. Sorry, we now have what have we done now? We have told that if it is a rotation matrix with a determinant, we have shown that it has determinant +1 and it's also orthogonal. And we have also shown there exists one eigenvalue whose value is equal to 1. There exists an eigenvalue with 1 as the magnitude. Therefore, 1 is an eigenvalue of A. Okay, any questions here? We will be computing the eigenvector and then making certain statement. There may be easier way to show. This is one sequence I.
No questions.
Yeah. So let us look at the eigenvectors now. Suppose V0 is the eigenvector corresponding to eigenvalue 1. Therefore, AV0 will become lambda times V0, but lambda is 1. So therefore, AV0 is V0. A rotation matrix is supposed to rotate the vector. Why it is not rotating this eigenvector corresponding to eigenvalue 1? For that, you look at this particular case. So let us look at this x-axis rotation. What does this mean? In this expression, the rotation is with respect to x-axis. The changes are observed in the y and z plane. So if you multiply this with 1, 0, 0, that is vector 1, 0, 0. You take this matrix, take a column vector 1, 0, 0. If you multiply it with 1, 0, 0 or a 0, 0, small a 0, 0 or any number x1, 0, 0, what will be the result?
Same. X1, 0.
It will be the same, right? So that means this x-axis rotation matrix will not change the vectors which are lying along the x-axis. The x-axis rotation matrix will not change the vectors lying along the axis of rotation. So what does it mean now when you have such an expression AV0 equals to V0? What does this? How do you now?
Axis,
V0 is
the axis of rotation.
very good. V0 is the axis of rotation. And what is happening? Very good. That's an excellent. V0 is fixed with respect to the rotation matrix. Fixed in the sense it is invariant with respect to rotation matrix. It is defined, it is called as the axis of rotation. Now you make one more observation. If you come back to this x-axis rotation, if you have a vector in the yz plane, after rotation, will it come out of this plane?
No, sir.
Yes or no? Actually, your voice is slightly low. Can you speak up?
No, sir.
Okay, no. So if you have a vector in the YZ plane, so YZ plane is orthogonal to X axis. If you have a vector in the plane orthogonal to the axis of rotation, and then if you try to rotate those vectors in the plane of orthogonal to the axis of rotation, it will not come out of the plane. So this is another abstract property of the rotation operation. Rotation operation preserves certain axis, certain vectors, which are called as the axis of rotation. And then if you have vectors in the plane orthogonal to the axis of rotation, even those vectors are also preserved in the same plane. One is it fixes, that is axis of rotation does not change, and the vectors in the orthogonal plane will lie on the same plane. So that is, let us try to show that here. So there is one more exercise you can show. Even V0 is fixed with respect to A transpose. That means the eigenvector of A transpose and eigenvector of A are same. You can go back and show it separately. I'm not going to show it here. Let us make this assumption. But we will show this one. Suppose you have a vector which is orthogonal to V0. That is, it is lying in the plane orthogonal to V0, which means that V0, V transpose V0 is 0. Now, if you rotate this vector by this rotation matrix A times V whole transpose V0, let us see what happens to this, is equal to V transpose A transpose V0. But this one by associativity, you can express it like this. That is A transpose V0. By the previous expression, we have shown that even V0 is fixed with respect to A transpose. So therefore, AV whole transpose V0 is 0. That means the vector AV is orthogonal to V0. If the vector V is orthogonal to V0, then the vector AV is also orthogonal to V0. That's what is shown here, which is what we also expected. An example is shown on the right hand side. Any question?
Sir,
Yes.
sir, can you explain this last one once again?
Okay, so for that, we will go back to this expression. If you have the rotation with respect to x-axis, so if you multiply it with any vector which lies only along the x-axis, what kind of vectors will they be? Can you describe at least one vector along the x-axis? Whoever asked the question, can you describe at least one vector along the x-axis?
I kept, sir. Unit vector.
Yeah, no, no, not in the abstract sense. Can you give me one realization of the vector along the x-axis in the standard coordinate system? Some example, how many vectors are there? There are infinite number of vectors, no? Can you give me one number, one set of numbers? Three
Okay.
sets of numbers, of course.
Okay. 5, 0, 0.
Very good. 5, 0, 0. So if you multiply this matrix with 5, 0, 0, what will you get as output?
5, 0, 0.
Okay. So what does it say? It says that 5, 0, 0 is just an example. Any vector, any such vector, if you had multiplied this matrix with, you would have got the same number. Do you accept that?
Yes, sir.
So that means along the x-axis, nothing is changing. So you can consider x as the axis of rotation. So that was the first conclusion we obtained earlier. Probably you understood that. I'm just reiterating that. So if you consider an eigenvector corresponding to eigenvalue 1, then you get A times V0 is equal to V0. That means any scalar multiples of V0 also will have the same property. You should observe that A times alpha V0 will be alpha times V0. So that means this vector V0 can be thought of as lying along the axis of rotation. Do you accept this?
Yes, sir.
Okay, so this is the key. Okay, so once that is accepted, somehow you can prove that even this axis of rotation is same for the A transpose. So one way to imagine this is A and A transposes are inverses of each other. Therefore, if V naught is not changed by A, how can the inverse of the matrix change this V naught? That is another way to look at it. But let us assume that you have somehow mathematically shown that A transpose V naught is also V naught. Can you make that assumption?
Yes, sir.
Okay, so now let us see what we are trying to imply here. In this expression on the right hand side with the rotation with respect to x-axis, if you consider a vector along the yz plane, if you consider a vector along the yz plane, how will you imagine that? You have to imagine this one as the yz plane and your x-axis is protruding towards you. That is one way to imagine. Can you imagine that?
Yes, sir.
Or to make the things easier, we can simply use the last expression. That is, let us imagine z-axis rotation. Okay, don't worry. I think since we started with x-axis, let us stick to that. You can imagine there is a plane which is orthogonal to the x-axis. If you had a vector along that plane, if you multiply this matrix with that vector, the first question that is asked is, will it come out of the plane? The components of the x is not changing. So what you do is you multiply this expression. What can you give an example of vector in the yz plane? What will be the component of the x for a vector in yz plane?
0, sir.
0. So it will be 0, comma y1, y2. Sorry, yz. Can you make that assumption? 0, yz.
Yes, sir.
So if you multiply this matrix with that vector, what will you get? Will you get any component in the x?
No, sir.
You won't get. That means any vector in the yz plane. And what is this yz plane? Yz plane is orthogonal to the x-axis, is kept in the same plane even after rotation. Do you agree with this?
Yes, sir.
Okay, so that is the same. Whatever we discussed now, we are trying to generalize it. Suppose you have a vector which is orthogonal to the axis of rotation, which is V naught. For us, if you have a general matrix, if V naught is the axis of rotation, AV naught is V naught, and A transpose V naught is also V naught. So let us consider all the vectors which are orthogonal to this vector. Let us take one example vector V. If V is orthogonal to V naught, V transpose V naught is 0. Is that right?
Yes, sir.
Okay, so now let us see what happens when we apply the rotation operation. So you multiply the vector in the orthogonal plane with the matrix A, which is your rotation matrix. After multiplication and expansion, you get these expressions. Is this expansion okay for you?
Yes,
So you
sir.
have confusion here, you tell. Usually what happens is in the beginning, you do not know how that initial step happened, but rest of the step will be simple.
No, sir. It's clear.
Okay. And then you can open out this braces also, right? Because matrix multiplication follows associative rule. Associative rule is an extremely important rule because of which all your left identity, right identity are same. All these things are happening. Okay. Maybe when we discuss about group theory, we can talk about it, but not now. But because of the associativity property, these braces can be opened up. That means V transpose can be separated out and A transpose V naught can be clubbed in. So that is done here. But what is A transpose V naught?
ರಾಮ ಗೂಗಲ್ ಆಫೀಸ್ ಅದೇ ಮಾಡ್ಬೋದು ಫೋಟೋ ತೆನ್ನು
What is A
0, sir.
transpose V naught?
0.
No, A transpose V naught.
V naught,
AV
sir. V naught. V naught, sir.
Yeah, V naught. But V transpose V naught is
0.
0, already shown. That means AV is your rotated vector and V was in the plane orthogonal to the axis of rotation V naught. So even after rotation, it is lying in the same plane. Is that okay? That is what we have shown here.
Yes, sir. I understood.
Yeah. So you have to imagine this. Whenever you get confused, no, you go back to this example. Always, you may have a complex abstract expression. You should have a simplest way to explain that. And one of the simplest way to explain that is using very trivial examples. And this is an extremely simple example which captures the gist of what we are explaining. And this is in the most generic way we have stated on the left-hand side. And the simplest way you can imagine is rotation with respect to one of the elementary axes. You may probably have to go back and think once or twice, you will get back. This abstraction always is slightly confusing, but don't worry about that. Once you imagine it for some time, it will come to you. So the statement is A times V is orthogonal to V naught. If V is orthogonal to V naught, A times V is also orthogonal to V naught. Is that clear?
Yes, sir.
Okay,
Yes, sir.
very good. Anyway, you can skim through it once again. This is very simple. How do you compute this thing? If you assume A matrix to have components A1, A2, A3, sorry, A11, A12, A13, and so on like that. So if you have to compute this eigenvector, you simply have to expand it. There isn't much here, just a straightforward expansion. If you solve A minus identity multiplied by V for the vectors V1, V2, V3, you will get this expression. Don't worry about it. This is not important. You can always solve in whichever way you want the eigenvector corresponding to eigenvalue 1 for a given matrix. So in case some of you may have excellent memories, you can directly use it and verify for one case. It's only for that purpose. Okay, if you don't have memory, don't worry. You simply have to know how to compute the eigenvector corresponding to eigenvalue 1. Okay, I am just pausing for some time. Any questions?
Sir, apart from eigenvector, eigenvalue and the other eigenvalue also, right?
There may be other eigenvalues. Later on, we will see that actually, okay, so if you go back to this expression, can you compute the eigenvalues of this for the x-axis one?
Yes, sir.
One of the eigenvalue is 1. So what are the other eigenvalues? We have to compute the eigenvalues of that smaller matrix. Have you seen such matrices somewhere? It's an important representation, okay? It's called rational canonical form. Later on, maybe whoever is going into mathematics major or something, or if you come deeper into control systems, you will come to that. What are the eigenvalues of that? Maybe we will take that digression now, because next class, you take this simple matrix, A minus B plus B, A. Can you compute the eigenvalues of this one? Minus can be anywhere, okay, in the diagonal, just off diagonal. Yes.
So 1 second.
Hmm?
So 1 second, sir.
Yeah, 1 second you said, okay. Your second is over, you should say 1 minute. Just joking.
A plus minus square root of a square plus b square
A
plus minus
hmm,
square root of a square minus a square a square minus a square plus b square. That means, okay, sir. I mean, IB.
yeah, tell me A plus or minus
IB, sir.
I
B.
B. Good. You look at this. It has complex eigenvalues. Okay, so this is one representation for complex numbers. If you have a complex number, you can represent it with a matrix. And it has an important application. Okay, this is also called that the number system expansion also. So you look at this real numbers. What are real numbers? This is a digression. Okay, the class is over now. Do you have a next hour class? This is not related to navigation. This is a generic thing. For those who are interested, I'm just trying to explain something. Okay, so otherwise your class is over. You probably can stop recording also. I will not do anything. We will discuss the remaining things in the next. What time is our lab starting?
2:45.
2:40. Okay, so those who are interested can stay back. Otherwise, if you do you have any class at 1:45
Yes, sir, we have.
on the same link? Huh? Okay. Okay, then I will stop. We will discuss this in the next class. Okay. So
Sir,
yeah,
sir, can we keep the lab at 3?
lab,
At 3, sir. 2 p.m.
no problem.
Okay, sir.
Okay, sure. So I think we can stop. Probably we will discuss some of these things there. Okay. Have a good day, everyone. Thank you.